Chapter 3. In Chapter 3, we will introduce you to exponential and logarithmic functions. We will first define what we mean by an exponential function, graph exponential function, and then consider applications which model exponential functions, including world population growth examples, earthquake intensity, and compound interest. In section 3.1, we actually define what we mean by an exponential function. So the exponential function f with base b is defined by f of x is equal to b to the x. B is the base. Or we can express this as y is equal to b to the x, where b is a positive constant, of course, other than 1. We also require that the base b be greater than 0 and not equal to 1. And the exponent x is any real number. All right? Examples. Let's look at some examples of exponential functions. Let's take the function f of x is equal to 2 to the x, where the base is 2, the exponent x, the variable x. Another example might include h of x is equal to 3 to the x minus 1. And another example, g of x is 1/2 to the x minus 1. Now that we know what an exponential function is, let's graph the exponential function f of x is equal to 3 to the x. All right, so we're going to generate a table of xy coordinates. So let's complete the table. And let's choose x to be minus 3, minus 2, minus 1, 0, 1, 2, 3. So we're going to complete this table. So when x is minus 3, I want to compute f of minus 3, which is 3 to the minus 3, which is 1 over 3 cubed, which is 1 over 27. Negative 2, computing f of a negative 2, I have 3 to the negative 2 is 1 over 3 squared, which is 1/9. When x is a negative 1, let's evaluate the function at a negative 1. So f of a negative 1 is 3 to the negative 1, which is 1/3. 0. F of 0 is going to be 3 to the 0, which of course is 1. When x is 1, let's find f of 1. F of 1 is 3 to the first, which is just 3. All right? 2, when x is 2, f of 2 is 3 squared, which is 9. When x is 3, computing f of 3, we get what? 3 cubed is equal to 27. All right, so we're going to plot these ordered pairs in the rectangular coordinate system to obtain the graph of f of x is equal to 3 to the x. So let's plot them. Negative 3 is 1 over 27. F of a negative 2 is 1/9. F of minus 1 is 1/3. F of 0 is 1. F of 1 is 3. 1, 2, 3. F of 2 is 9. 4, 5, 6, 7, 8, 9. And f of 3 is 27. So we obtain the graph by connecting the points. All right, so this is the graph. F of x is equal to 3 to the x. In the next example, again, we want to graph an exponential function. Let's graph the function f of x is equal to 1/3 raised to the x power. We also know that we can rewrite this as really 3 to the minus 1 raised to the x, which is just 3 to the minus x, if you like. All right, in order to graph the function, we need to generate a table of x, y values. So let's see, we have x and f of x is 1/3 x, which is 3 to the minus x if you want to use it. Let's choose the x values. Negative 2, negative 1, 0, 1, 2. All right, so we're going to evaluate the function f at each of these x values. So in the first case, when x is a negative 2, I want to find f of a negative 2. F of a negative 2 is going to be 3 minus a minus 2, which is 3 squared, which is 9. When x is a negative 1, I need to now evaluate the function at a negative 1. So f of a negative 1 is going to be 3 minus a negative 1, which is 3, which is just 3. Okay? 0. When x is 0, we have f of 0. F of 0 is going to be 3 to the minus 0, which is, of course, 3 to the 0, which is just 1. F of 1. F of 1 is going to be 3 to the minus 1. 3 to the minus 1, as we recall, negative exponents, this is 1/3. When x is 2, evaluating the function f at 2, we get 3 to the minus 2, which is 1 divided by 3 squared, which is 1/9. Now that we have ordered pairs, we can obtain the graph of the given function by plotting the ordered pairs in the rectangular coordinate system. So let's see what happens. When x is a negative 2, we get 9. So a negative 2, 9. When x is a negative 1, we get 3. 1, 2, 3, negative, okay? and 0, 1, 1, 1/3. When x is 1, y is 1/3. When x is 2, y is 1/9. All right, we can see that the points are getting closer and closer to the x-axis. So now we connect the points to obtain the graph. All right, so this is the graph of the function f of x is equal to 1/3 to the x. All right, in the next example, we will use the graph of f of x is equal to 3 to the x to obtain the graph of g of x is equal to 3x to the minus 1. All right, so let's look at the two tables first, and then we'll talk about the transformation of the graph 3 to the x to obtain the graph 3 to the x minus 1. But if you wanted to check, let's just first create a table of values for the two functions. And then we have g of x. We have 3 to the x minus 1. All right, so let's choose x to be a -2, -1, 0, 1, 2. When, for the first function, f of x is equal to 3 to the x, well, we just graph this function. So that's 3 to the minus 2, which is 1/9. 3 to the minus 1, 1/3. When x is 0, 3 to the 0 is 1. When x is 1, 3 to the first is 3. And when x is 2, 3 squared is 9. For the other function, g of x, the function is defined to be 3 to the x minus 1. So when x is a -2, we have 3 to the minus 2 minus 1, which is 3 to the minus 3, which is 1/3 cubed, which is 1/27. When x is a -1, we now want to find g of a -1. So when x is a -1, I have 3 to the minus 1 minus 1. So we have 3 to the minus 2, which is 1/3 squared, which is 1/9. So the y coordinate is 1/9. When x is 0, I have 3 to the 0 minus 1, which is 3 to the minus 1, which is 1/3. When x is 1, we have 3 to the 1 minus 1, which is 3 to the 0, which is 1. When x is 2, we have 3 to the 2 minus 1, which is 3 to the first, which is just what? 3. All right, so now we can plot these, of course. So let's see what happens. So if we plot, we have for f, let's plot f first. When x is a -2, we have 1/27. When x is a -1, we have 1/9. When x is 0, we have 1. When x is 1, we have 1. When x is 0, we have 1. Let me make sure I'm doing these. Let me go back. -2, 1/9. Minus 1, 1/3. 0, 1. 1, 3. So when x is 1, y is 3. When x is 2, y is 9. So 3, 4, 5, 6, 7, 8, 9. All right, so we connect the points. All right, so this is the graph of f. All right, to graph g, well, we have the coordinates, the x and the y coordinates for g. We could also graph them. All right, and if we did that, we would obtain what? For -2, we got 1 over 27. Okay. For -2, 1 over 27. When x is a -1, 1/9. 0 is 1. 0 is 1/3, sorry. For g. But 0 is 1/3, so it's about here. All right. And when x is 1, y is 1. So 1, 1. And 2, 3. All right, over 2, up 3. All right, if we connect. All right, so this becomes g. All right, now, that's one way. That's the traditional way, but we've also studied transformations of functions. So we can also obtain the graph of g of x by what? By shifting, if you notice, this is f. So if we shift the graph of f 1 unit to the right. So let's say it's here. So if I come over 1 unit, it's here. So we have the point 1, 1. All right, so that's one way of obtaining the graph by shifting the graph of 3 to the x 1 unit to the right. All right, in the next example, we want to introduce you to the natural base e, where the irrational number e is the actual base. But before I do that, let's just for all exponential functions of the form b to the x, let's review some of the characteristics. All right, we said that the domain of the exponential function in this form would be what? All real numbers. The range would be all positive real numbers. And we noticed that what? When x is 0, b to the 0, so the graph goes through the point 0, 1. So in other words, 1 is the y-intercept for any exponential function expressed in this form. When b was greater than 1, for instance, we had f of x is equal to 3 to the x. All right, where the base is greater than 1, we notice that the function was what? It went up, so it's an increasing function. And when the base b, remember we also had f of x, we graphed 1/3 to the x. All right, in this case, we saw that the function was what? All right, it was a decreasing function. All right, when we graphed that, it looked like this. All right, so when b is less than 1, the function is decreasing. And we also noticed that in each case, we got, all right, using the horizontal line test, we see that the exponential function indeed is 1 to 1, therefore it will have an inverse function. And we also saw in all cases that the x-axis served as the horizontal asymptote. All right, with that said, let's consider now the graph of the natural base, y is equal to e to the x. We know that e is an irrational number between e is an irrational number, all right, which is approximately 2.71. All right, so in order to graph this function on the exponential function with base e, the natural base e, all right, so we need x again, and we need y is equal to e to the x. All right, now again, let's choose x values to be -2, -1, 0, 1, and 2. All right, so to get the corresponding y coordinate, so for x is -2, I'm going to have e to the -2, which is 1 over e squared, which is 1 over 2.71 squared, which is approximately 1 over 7.38, if you like, and I'm getting 0.135. When x is -1, we have e to the -1, which is 1 over e to the first. So that's 1 divided by e. E is approximately 2.71. When you do that division, you get approximately 0.369. When x is 0, we have e to the 0. We know that's 1. When x is 1, e to the first, which is just e, which is again approximately 2.71. And when x is 2, we have e squared, which is 2.71 squared, which is approximately 7.38. So now that we have x and y coordinates, we can obtain the graph of e to the x by just plotting the points in the rectangular coordinate system. So for -2, I have a 0.135 for -1, 0.369. When x is 0, we get 1. When x is 1, we get 2.71, about here. And when x is 2, we get 7.38. 1, 2, 3, 4, 5, 6, 7, about here. All right, connecting the points. It's a horizontally, you know, okay, it's, all right. All right, so this is the graph of y is equal to e to the x. In the next example, we want to consider an application of exponential functions. Let's look at compound interest. And compound interest helps us understand how money in savings accounts grow at a remarkable rate. All right, as a result of what? Compound interest. Compound interest is interest computed on your original investment, as well as on any accumulated interest. All right, so what we have here, we have, all right, in this case, the amount or the balance in the account is going to be A, where A, of course, A is the amount in the account. P is the principal, the original amount of the investment, principal, the original amount of your investment. R is your rate of interest. All right, R is the rate of interest. All right, and N, all right, N is the number of compounding periods per year. So the number of compounding periods per year. For instance, if you compound annual, well, it's not compound, that's simple interest, but if you compound semi-annually, N is 2. All right, or you can compound quarterly. In the next example, and T, of course, let's say that after so many years of investing and compounding, after 3 years, how much is in the account? So T represents that time period after, say, so many years. All right, after T years. All right, so the first formula is for, this one is for N compounding periods per year. All right, and in the next one, all right, still the same formula, but this time we are compounding what is called continuously. So continuous compounding. All right, and notice in this formula, we're using the base, the natural base E. All right, so the amount in the account is A is equal to P times E to the RT. Now, as an example, I would like for you to complete for homework checkpoint number 7 on page 423 in the textbook. And if you have any questions, you want to post those questions, of course, to the discussion board. All right, so you should let me know that you understood checkpoint number 7. If you have any questions, please post them to the discussion board.